Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my fourth video on the Millennium Prize Problems. As I mentioned in my previous videos, there are seven Millennium Prize problems altogether. Six of them are all unsolved still, and there's $1 million prize for anyone who can solve any one of them. The seventh one has already been solved. It was solved in 2002 by Gregory Perlman, who turned down the prize for some strange reason. But anyway, today I'm going to talk about the Navier-Stokes existence and smoothness. This is one of the problems. So on this slide, I show the Navier-Stokes equations. These are two equations of differential equations for fluid flow, general fluid flow. So anyway, what's not known is whether for every set of initial conditions, in this case, they're writing U for velocity, or usually people write V. So V0 is the initial velocity. I'll get to this later, but anyway, the upshot of this problem is to either prove that there always exists solutions given any initial velocity of your fluid in 3D, or to show that there are certain velocities for which there are no solutions. That's the idea. So anyway, let me give you a little bit of historical background first before I go into the Navier-Stokes equations. And keep in mind that I'm not an expert on this. I mean, I have studied a lot of physics, but I think the one area of physics I really didn't study much was fluid flow. I guess it just never came up in the area of physics that I was studying. I was interested in high energy physics and not so much material science or fluid science. But it is important, and so the kind of the starting point in understanding how fluids behave, I think, was Daniel Bernoulli. He was one of, I think, eight or nine family of amazing mathematicians around the late 17th and early 18th century. All of these guys made some pretty amazing contributions to mathematics or physics. In particular, Daniel Bernoulli came up with what's called the Bernoulli's Principle, which applies to, it's a special case where it applies only to incompressible and what's called inviscid flow. That means flow with no viscosity. And it's a very good approximation to a lot of fluid flow that we study. For instance, it's good enough for aircraft, at least to a first approximation. And Bernoulli's principle, in particular, can be used to explain how airplanes work, how they fly. It's Bernoulli's principle. You get a lift because of the shape of the wings of the airplane. You get a higher pressure below on the bottom of the wing than on the top, and that gives the plane its lift. That's how planes fly. And Daniel Bernoulli discovered that. So we kind of owe airplanes to Bernoulli, Daniel Bernoulli. And then that was kind of the first step. The next step was done by Euler shortly afterwards, 1757. He came up with some more general equations of fluid flow. We're no longer do we need to assume that the flow is incompressible. It could be compressible, which is a good, because gases are compressible. I mean, liquids are to a very good approximation incompressible. So I guess Bernoulli's principle can apply more generally to liquids than to gases. But if you want to model gases more accurately, you have to assume they're incompressible, and then you get Euler's equations. And these were further modified by Lagrange and other. These are all really great mathematicians, by the way. Lagrange in 1816 further generalized Euler's equations to the case where you have adiabatic flow, and I'm not going to explain what that is. But anyway, so these pretty much apply to gases, and then if you want to include viscosity, that's where things get really complicated. But that's what the Navier-Stokes equations are all about. So these were two guys. One was a French mathematician named Navier. He modified Euler's equations in 1822, and then independently, an Irish mathematician named George Stokes did the same thing. I guess it took him 8 years, but he came up with his own set of equations from 1842 to 1850. And I'm not sure how this worked. I think they kind of independently discovered the same equations for general fluid flow. So now it could be viscous as well as inviscid, and compressible as well as incompressible, which I think pretty much covers every kind of fluid. But here, I couldn't resist putting this slide in here. Bernoulli's principle, which basically says you can apply it to pipes too. I mean, you probably know that if you have a water pipe with a neck, the fluid will flow faster through the neck. Just because the fluid's incompressible, it has to flow faster just to conserve the volume. And you can see the general equations on top of this slide. You don't really have to use much math or physics to derive these equations. It's really just conservation of energy applied to fluids. I've done this. I learned this in undergraduate class I took a long time ago. They're not that hard to prove. And then I couldn't resist leaving showing pictures of Navier and Stokes. There's Claude Louis Navier on the left and George Gabriel Stokes on the right. Stokes is famous for one more thing, by the way. The Stokes, what is it? I think it's called Stokes Law. Yeah, which is a special case of, or actually, I think Green's theorem, the Stokes theorem for integration. Um, anyway, that's not really part of the scope of this video, so I won't mention that one. I just mention it, but it's an important law in physics. You can apply it to electricity and magnetism, by the way. I think Ampere's law is a consequence, or Biot-Savart law, the consequences of Stokes' law. But he also did the Navier-Stokes equation, and here it is written out. I'm not going to go through this slide in details. You can see it's a pretty complicated equation. It's a second-order differential equation, partial differential equation, which many equations in physics are. But like I said, I never really studied this equation. I'm not an expert on it. Basically, the same equation I showed on the first slide, a little bit different notation, though. And also, I think divide by rho. Rho is the density. So it's really just telling you that, I mean, you're supposed to think that V is the velocity of the fluid. It's kind of the speed and direction of every point in the fluid. So you can think of the velocity as a vector field. And this equation just tells you how the velocity of the fluid evolves with time given its initial conditions, its density, this thing, the upside down triangle, that's called a gradient. So it depends on the gradient of P. I think P is the pressure, and then you have this thing, rect side up, delta. I prefer to write this as upside down delta squared. That's what's called the Laplacian, I think, or Lagrangian. I can't remember. It's been a long time since I studied this stuff. It's basically I think it's Laplacian. Yeah. Anyway, so that's the equation. This F is a force term. So I pretty much told you what everything is in this equation. And so this equation is known to hold for general fluids, but what's not known is whether this equation is always solvable. And there's actually another equation as well on the bottom of the slide. I think this is this conservation of fluids, just saying that the fluid can't be created or destroyed. I think that's what that one says. Yeah, conservation of mass. So you can't create or destroy fluid in your system, which is a reasonable assumption. I mean, we're not assuming that energy is getting converted to matter here. That would make things even more complicated, but I don't think we've ever studied a fluid where that happens, so we don't have to worry about that. We might when we're dealing with plasmas if we're trying to work on fusion or something, but we don't have to worry about ordinary fluids. And all the rest of this slide is showing is that these are really, it's a system of equations. I mean, this is a vector equation on top. So you can write it as a system of scalar equations, which is what they do on the bottom. Really the same thing, just written out in a different form. So that's the statement of the Navier-Stokes equations. And then the statement of the problem is basically so we have two assumptions about our fluid. The written is assumptions 1 and 2, and I'm not going to go through those. I think they're just saying that the fluid is behaving kind of nicely. The velocity doesn't go to infinity anywhere. It's finite everywhere, and the pressure is finite everywhere too. It's well behaved. These are well behaved functions basically. Not there's no discontinuities in them. So I think those are kind of the assumptions, and also that I think that velocity has some nice integration properties. Anyway, so if you assume these assumptions about the fluid, which are pretty reasonable assumptions, I think, then there's two possible ways you can solve this problem, this Millennium Prize problems. There's A is existence and smoothness of the Navier-Stokes equation. So what this is saying is that for any force term and any initial velocity v0, as long as you satisfy conditions 1 and 2, it's saying that there is a solution, that there does exist a unique solution to the Navier-Stokes equations in this case. So for every initial condition you can give it, as long as it satisfies these nice conditions, there is a solution, and I think we could solve it, at least in principle. So that would be one way you could solve this Millennium Prize problem. The other way is you could prove that there are certain initial conditions for which you can't solve it. So that would be a negative result. It would say that there are some initial velocities for which there is no a computable solution, or maybe you get chaos, maybe you get turbulence that you can't predict. Who knows? But so those are the two possibilities. Either there does exist a unique solution that we can solve, or there doesn't. And there's a prize, there's $1 million prize for either solution. I guess the people who offer the Millennium Prize problem don't care if you prove it or disprove it, because it'd be really interesting in both cases. And I'm just going to talk a little about why we care. I think I already kind of hinted at this. I think the main reason is understanding turbulence. Because even though we've been studying fluids for something like 300 years, and we've had Navier-Stokes equations for almost 200 years, we still don't understand turbulence. And turbulence is an important problem. I mean, I think you guys have all experienced it when you've flown on certain, airplane flights. You hit turbulence, they don't expect it, but all of a sudden, the plane starts bouncing up and down. Sometimes it can be pretty violent. So it'd be nice if we could understand turbulence better. We might even know how to avoid it, for airplanes. So that's a practical need. I'm sure there's other situations where turbulence is important. You want to avoid it. I think that's the main motivation, to understand turbulence. And then there've been a bunch of partial, although nobody's solved the Navier-Stokes equations in general. There have been a lot of progress on this problem. I'm just going to outline what's already been done on it. So first of all, we've been able to apply finite difference methods, in other words, numerical methods, at least in 2D. This was starting in the 1960s. So in the 1960s, I guess we had the first computer models of fluid flow in 2 dimensions. I don't think they did it in 3 dimensions, probably because it was too complicated at that time. Maybe they've done it in 3 dimensions now. I don't know. Probably have. But, so they were able to use some finite difference methods to successfully solve, I think, for all initial conditions in 2D. I think they were able to numerically solve the Navier-Stokes equations, which is very encouraging. I don't know if they could do it in 3D, though. That I don't know. I'm guessing not, because I think that would count as a solution. I'm not sure if it would. I don't know if the Millennium, the people offering this Millennium Prize care whether you solve it numerically or analytically. I don't know about that. My guess is it hasn't been done numerically in 3D. And then the second item on here, it was proven that as long as your velocity is small enough everywhere, then there does exist solutions. So there are solutions to the Navier-Stokes equations as long as the velocity of the fluid is small enough. I guess you reach some threshold and then you can't solve it anymore. At least we don't know how. And then number three, so you can do it for general velocities, but then there's a blow up time. So two and three are kind of nice results because they're sort of hinting that maybe there is a general solution. First of all, two says you can solve it as long as the velocity is not too big. Three says you can solve it for any given velocity up to some time threshold. They call that the blow up time. I guess there's some critical time where things blow up and you can no longer predict it. But at least you can predict it for a certain interval of time. And then number four, there was a mathematician named Jean Levy in 1934 who was able to find what he called weak solutions to the Navier-Stokes equations. These are not solutions at every point. They're sort of averaged out solutions. So he showed that you could solve the Navier-Stokes equations sort of, you could, solve it for regions. You could sort of smooth things out, I guess, and say that, your velocity over some finite region is approximately this or averaged over this region is this, but you can't solve it exactly at any given point. Yeah, and so these are all important partial results. And finally, in 2016, Terence Tao, who I think is widely regarded now as one of the greatest, maybe the greatest living mathematician. He's an amazing mathematician, a young guy too. But he proved that I think he kind of extended the work of John Levy. He showed that not only could you find these averaged out solutions, but you could um, uh, um, you could what did he do? He said that you could he found specific solutions. That was the first thing he did. He used some method. I don't know what his method was, but he found some specific methods for finding nice averaged out solutions up to some given blow up time. And he says that his methods could be modified so that you could extend the blow up time to infinity, basically. So I think he knows a way to solve this. And he actually may win the Millennium Prize Problem for this, the $1 million for solving this. I think he believes, as far as I understand this, that there is a solution to A. He can prove existence and uniqueness, and that'd be great. So he'll win $1 million for this, as long as he doesn't turn it down like what's his name, the Russian guy who turned down the one for the Poincaré conjecture. I can't remember his name right now. But anyway, so now the last thing I want to talk about is just some references in popular culture. Apparently, there was a book that came out in 2014 called The Mathematical Shiva. And it's a fictional, it's a fictional novel, but it's about, I guess, a female mathematician who was very angry at I guess at her college, at the academic institutions, and she solves the Navier-Stokes equation, but she doesn't publish it. She holds on to it until she dies because she doesn't want the university to have the knowledge that she discovered it. Sounds a little like I wish I could remember that Russian guy's name now. Geez, I mentioned him earlier. God, it's bothering me. I can't remember his name. But maybe he turned down the prize for similar reasons. I don't know. And then they used pretty much the same plot in a 2017 movie, which I've seen. I've actually seen this movie a couple times. It's called Gifted, and it's a very good movie. It's about a 7-year-old female math prodigy, and she I guess her mother had died, but her mother had solved. I guess the mother was supposed to be like the mathematical Shiva. It turned out at the end of the movie that her mother had actually solved the Navier-Stokes equations, but she never published her solution. But she kept the notes for her daughter. She wanted her daughter to publish the solution, even though she didn't solve it herself. So I don't know. It's kind of weird. I mean, I don't know what's with mathematicians. It seems like, I know that Perlman. Now I finally remember his name, Gregory Perlman. I don't know why he turned down the prize. And this also reminds me of another movie, really good movie called Good Will Hunting. It's a very popular movie about another fictional story about a mathematical prodigy played by Matt Damien, and he solves this almost impossible math problem, but he keeps it a secret until the very end of the movie when Robin Williams kind of convinces it to let down his guards. So I don't know what's with mathematicians. I mean, I know that mathematicians are not very well revered in our society. I know this for a fact, both based on my own personal experience, also based on a lot of what I know about a lot of mathematicians. I mean, think about it. I mean, probably one of the greatest mathematical results of all time was the proof of Fermat's last theorem, which was just proved about 30 years ago by Andrew Wiles, and still most people don't even know who he is. And a lot of mathematicians have done strange things. I mean, like the Unabomber. I think the Unabomber is probably just about the only mathematician that most people in our society know, which is very sad, I think. He was a genius. He was a genius too. He went to Berkeley, which is where I was at school, not at the same time as me. But, he got caught when I was in graduate school at Berkeley. I don't know what made him go crazy. I don't think anybody does. But he must have been very unhappy about something or other, that made him go berserk. And I can kind of testify to that a little bit myself. I mean, I actually had a nervous breakdown in 1989. I didn't do anything, I didn't hurt anybody. I didn't break any laws, but I trashed my apartment and I ended up in the hospital for a month. And I think a big reason I had that nervous breakdown was I was trying to learn string theory. I was studying physics at the time. I didn't get very far with it. I was also very depressed. But, I don't know what it is with mathematicians, but I don't think it's just the mathematician's fault. I think a lot of it's the fault of society, too. We're not a well revered profession. I mean, look at it. I mean, celebrities, like Taylor Swift, she's already a billionaire. And, our president, billionaire. And he's also a felon. And O.J. Simpson, killed two people. Everybody in the world knew who he was, I mean, people don't know mathematicians, and I wish they did. But I'll tell you something. If I ever solve a Millennium Prize problem, which I don't think I ever will, but if I ever did, I would take the $1 million. I mean, we've got it bad enough. We might as well take the money and run, right? I mean, if we can solve a big problem and get fame for it and get a lot of money for it, then take the money, do whatever the fuck you want afterwards because we deserve it, okay? We deserve to be revered in our society. That's what I think. Anyway, enough preaching about that. But if any of you guys solve the Millennium Prize, any of these Millennium Prize problems, please let me know because I'm gonna be very happy for you if any of you guys can solve any of these problems. I also would strongly urge you to take the $1 million and do whatever the hell you want with it because I trust that most mathematicians are good people and you'll do the right things with that money. So anyway, enough preaching about all that. Anyway, I guess that concludes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.